Next, we will take a look at the conjugate addition to alpha-beta unsaturated carbonyls, which is the product from the aldol condensation. So here is an example of alpha-beta unsaturated carbonyl. We have a double bond next to a carbonyl carbon, and the two double bonds here are conjugated. When we have a nucleophile reacting with a carbonyl group, previously we've learned that a nucleophile will attack on the carbonyl carbon, open the CO double bond. So as a result, the final product will have an alcohol functionality. This reaction, we call it a 1,2 addition reaction. It's a direct addition, meaning the carbonyl attacks on the carbonyl carbon directly. And the 1,2 refers to oxygen is atom 1, carbon is atom 2. We are adding things to atom 1 and 2. Okay, atom 1, oxygen, gets a proton. Atom 2, carbon, gets the nucleophile. Next, we will take a look at another possibility. For alpha-beta unsaturated carbonyl, the nucleophile may be able to attack on the beta carbon, the terminal carbon in the system. The CC double bond will break, and the electron will go to the carbonyl carbon, and the carbonyl CO double bond will break. So in this process, the double bond shifted, and we are adding the nucleophile to a beta carbon. At the same time, the oxygen is able to pick up a proton from the solution. And this intermediate is actually the enolate. And when the oxygen gets a proton, it forms the enol, right? And we've learned that enol is not stable, so the enol will tautomerize to the keto form. So here is the final product. Carbonyl stays, and the nucleophile is attached to the beta carbon. This is called 1,4 addition, or conjugate addition, or Michael addition. 1,4 refers to atom 1, the oxygen, and atom 4. If you count from oxygen as 1 and the carbonyl carbon 2, alpha carbon 3, beta carbon 4. So oxygen atom 1 gets a proton, beta carbon 4 gets a nucleophile. The addition takes place on carbon 4 and oxygen 1. That's a 1,4 addition. The final product has the carbonyl. That is because the enol form is not stable. It goes to the keto form. Okay, so that's the conjugate addition, or the Michael addition. So for the alpha-beta unsaturated carbonyl, we have two electrophilic sites. One is the carbonyl carbon, the other is the beta carbon. 1,4 addition is favored when we have strongly basic nucleophiles, such as Grignard reagent or the oxnolithium reagent. With Grignard or oxnolithium reagent, nucleophilic addition to the carbonyl will take place. And 1,4 addition will be the major reaction when we have weakly basic nucleophiles, such as cyanide, enolate ions, or the oligocopper reagents. So I hope this will help you to distinguish 1,2 and 1,4 addition. 1,2 addition, stronger nucleophiles. 1,4 addition, weaker nucleophiles, more stable product. Let's take a look at an example here. So we have two starting material. One is the second one, an alpha-beta unsaturated carbonyl. And the first one is a diketone. When the diketone is treated with a base like potassium hydroxide, the carbon that is in between the two carbonyls will have the most acidic proton. Okay, the carbon in between. So the enolate can form, and the enolate is stabilized by the two carbonyl compound. And the enolate will have the conjugate addition to the alpha-beta unsaturated carbonyl. And here is the product right after the addition. So here is the structure of the enolate. The negative charge is shared by two oxygens, so you can draw two more resonance structures of the enolate. And this enolate will attack on the beta carbon of the alpha-beta unsaturated carbonyl. A new carbon-carbon bond is formed here. And the enol formed will tautomerize to the ketone, the final product. All right. The other aspect of the conjugate addition is that the product of this Michael addition has the necessary functionality to undergo an intramolecular aldol condensation. What do I mean by that? Here is the product from this conjugate addition, this Michael addition. Remember, in aldol condensation, it's the enolate of one carbonyl reacting with the other carbonyl. In this particular molecule, we have 3 carbonyls, right? The carbonyl in the ring could serve as the carbonyl compound, while the newly added carbon chain, this carbonyl could serve as the enolate. So when it's treated with a strong base, it's going to cyclize to form another 6-membered ring. How does this happen? The enolate is formed from the terminal methyl group. The proton on that carbon will be removed to give the negative charge. Then the negative charge will attack on the carbonyl carbon in the ring. This is how you build up a 6-membered ring. All right. So once the product is formed, dehydration can lead to the aldol condensation product. So for this conjugate addition of an alpha-beta unsaturated carbonyl with an inolate, we can form a cyclic product after an intramolecular aldol condensation. All right, so I'm going to stop here. I think you've got enough today to think about. I want you to work out the mechanisms of the reactions that we have talked about. See if you can get the product or explain how the product is formed. All right?